What is consciousness? For most of history, that question belonged to philosophers, and plenty of scientists thought it always would, that it was simply too slippery, too subjective, to ever pin down in a laboratory. Then in 2001, two French neuroscientists, Stanislas Dehaene and Lionel Naccache, published a paper that changed the terms of the debate. Their argument was disarmingly practical. Stop trying to define what consciousness ultimately is, and start measuring what it is, what a conscious mind can accomplish that an unconscious one cannot. Do that carefully, and consciousness becomes an ordinary, tractable scientific problem. This is the paper that launched the global workspace theory. Their strategy has 2 steps, and it's worth appreciating how clean it is. Step 1, gather the experimental facts that were already piling up in psychology and neuroscience, the ones any serious theory of consciousness would have to account for. Not speculation, just robust findings. Step 2, propose the simplest architecture that could explain all of them at once, and then insist that this architecture make new predictions that could be tested and potentially proven wrong. That's the shape of ordinary science, applied to a question people had treated as untouchable. Let's start where they did with the 3 facts. They isolate 3 major empirical observations. First, an enormous amount of mental processing happens entirely without consciousness. Second, attention is a prerequisite for consciousness. A stimulus can be perfectly strong and clear and still never reach awareness. And third, consciousness is genuinely required for a specific, surprisingly short list of mental operations. Everything else the mind can apparently do on autopilot. Each of these was established by careful experiments, and each one constrains what a theory can look like. Together they set up a puzzle. If the unconscious is so capable, what exactly is consciousness for? Let's take them one at a time. The first fact is humbling. Consider blindsight. Patients with damage to primary visual cortex sincerely report seeing nothing in part of their visual field. Ask them to guess where a light appeared or to point at it, and they protest that it's pointless. They see nothing. Yet they perform well above chance, and some perform as well as healthy controls. Or take masked priming in ordinary people. Flash a word so briefly, sandwiched between masks, that the person swears they saw nothing, and that invisible word still speeds up their response to a related word afterward. It was processed all the way to its meaning, an entire stream of processing, invisible from the inside. So if unconscious processing is that powerful, what determines whether something becomes conscious? The obvious guess is stimulus strength, make it bright enough and long enough. But that turns out to be wrong, and this is the second fact. Take the attentional blink, show a rapid stream of words, and if a second target appears within about half a second of the first, people simply don't report it, even though it's perfectly visible and would be trivially reportable on its own. Or change blindness, where enormous alterations in a photograph go completely unnoticed unless attention lands on them. The stimulus was strong enough. Attention was the missing ingredient. That sharpens the puzzle. If so much runs unconsciously, what work is left for consciousness? The third fact gives a precise answer, a short but crucial list. First, durable maintenance, holding information actively in mind after the stimulus is gone, keeping it alive over seconds. Second, novel combinations of operations, chaining together mental steps that were never previously wired to each other, improvising a new procedure. And third, the spontaneous generation of intentional behavior, using information strategically and deliberately rather than reflexively. Notice what these have in common. They all require information to be shared flexibly across many different mental systems. And that shared requirement is the key that unlocks the theory. Dehaene and Naccache propose the global neuronal workspace. The picture goes like this. At any moment, the brain runs a large collection of specialized modular processors in parallel. Vision, language, motor control, each doing its job locally and unconsciously. Most activity stays confined that way. But information becomes conscious when the neural population representing it is mobilized by top-down attentional amplification into a brain-scale state of coherent activity, spanning many distant regions at once. Once that happens, the information is globally available, and that global availability, they argue, is precisely what we subjectively experience as being conscious of something. The mechanism rests on a specific anatomical claim. The brain contains a population of neurons with unusually long-distance axons, ones that reach across the cortex rather than staying local. They're especially dense in the prefrontal cortex, the anterior cingulate, and the parietal areas connected to them. These are the workspace neurons. Here's the crucial point about their role. They don't do the computing. They don't recognize a face or parse a sentence. Their job is to make whatever a local processor has computed available to every other processor at once. They are the brain's broadcasting system, connection rather than calculation. Consciousness, in this account, is a matter of wiring. To show the idea actually works, they built a small simulation, and this diagram captures its logic. You have a feed-forward cascade of processors, information flowing from one to the next, exactly the unconscious pipeline. But one of those processors also participates in a long-distance reciprocal loop with a distant workspace network. That loop is the whole architecture. It lets activity feed back on itself, sustaining and amplifying rather than just passing through. Each unit is modeled with simple nonlinear dynamics. It's a deliberately minimal setup, and the striking thing is how much of psychology of consciousness falls out of it automatically. Here's what that simulation produces, and it's the theory's signature prediction. Give the network a brief, weak input, a sub-threshold stimulus, and watch. Activity ripples through the processors, doing real work, but the workspace shows only a small, fleeting flicker that dies away. That's a masked prime, processed but never conscious. Now make the input slightly stronger or longer, and something dramatic happens. Instead of scaling up smoothly, the system snaps. There's a sudden transition into a long-lasting, self-sustaining activation across both processors and workspace. That abrupt, all-or-none jump is what the field came to call ignition, and it explains why conscious perception feels like a threshold. Either you saw it or you didn't. The model also explains something subtler that any good theory of consciousness has to handle. Present the exact same borderline stimulus many times, and people's reports vary wildly. Sometimes total blindness, sometimes a vague sense that something was there, occasionally a clear glimpse. If awareness were a simple function of stimulus strength, that shouldn't happen. But in the simulation, the same subthreshold input produces workspace activity of varying intensity and duration from trial to trial because of ongoing spontaneous fluctuations in the network. Whether you cross into ignition depends on the brain state you happen to be in. Subjective variability isn't noise in the data, it's a prediction of the model. A framework is only science if it can be wrong, so they spell out what the workspace model forbids. These three schemas lay it out. In the first, a fully automated stimulus response chain runs to completion unconsciously, while the workspace is busy elsewhere. That's allowed. In the second, something more interesting, even a task requiring selection between processors can run unconsciously, provided a conscious instruction set up the circuit beforehand. That's allowed too, and it neatly explains why unconscious effects can look surprisingly smart. They're running on rails that consciousness laid down earlier. But the third case is the one that matters. The third schema is labeled, bluntly, an impossible situation. It shows an unconscious stimulus reaching up and exerting top-down control, reconfiguring how the brain processes things on a trial-by-trial basis. The workspace model says this cannot happen. Why? Because to exert top-down control, you must engage the workspace, and engaging the workspace for any meaningful duration is exactly what makes information globally available, which is to say conscious. So if a stimulus genuinely reconfigures strategy on the fly, it must be reportable. That's a sharp, risky prediction, and it's the kind of claim that made this a scientific theory rather than a story. Then they checked the prediction against real brain imaging, and the picture holds up remarkably well. Tasks that demand exactly the operations they said require consciousness, effortful reasoning, novel sequences, error processing, reliably activate a consistent long-distance network centered on prefrontal and anterior cingulate cortex. And as a task becomes automatized with practice, that same network quiets down. The workspace disengages once you no longer need it. The cleanest test is binocular rivalry, where each eye sees a different image and awareness alternates. while the input never changes. The workspace network tracks what the person is conscious of, not what's on the retina. Looking back, it's hard to overstate what this paper did. It took a question widely regarded as beyond the reach of experiment and turned it into a concrete research program with an architecture, a mechanism, and falsifiable predictions. Its vocabulary, ignition, broadcast, global availability became the standard language of consciousness science, and there's a striking coda. 25 years later, researchers studying large language models went looking for exactly this structure inside artificial neural networks, a small privileged set of representations broadcast widely, supporting report and flexible reasoning atop a mass of automatic processing. They found something remarkably like it. The framework Dehaene and Naccache built for the human brain became the lens through which we now examine machines. Thanks for watching.